Greetings fellow designers and welcome to another video of Guidance Sorcery. This video is a beginner's guide to assembly modeling in SOLIDWORKS. If you are new here, I previously covered the basics of part modeling. I'll leave a link in the description below and a card at the top for easy access. It's essential to watch that video first, as it lays the groundwork for what we'll cover in this video. We will focus specifically on assembly modeling, keeping things concise and to the point. But before we begin, make sure to hit the like button and subscribe to my channel for more SOLIDWORKS content. As we've already learned, SOLIDWORKS features three main document types: parts, assemblies, and drawings. In this video, we'll focus on assembly modeling. For those who may be unfamiliar, an assembly document is essentially a collection of components brought together, allowing for interaction and motion between them. To begin a new assembly document, simply go to the File pull-down menu, select New, and then choose Assembly from the window that appears. Once the assembly document is open, you'll notice that the user interface is identical to what we saw in part modeling. This means you won't need to relearn the interface. Everything, from rotating the view, zooming and selecting objects, works exactly the same as it does in the part modeling environment. Also, the mouse and keyboard controls remain unchanged. Usually, when you open a new assembly document, the Open window might appear alongside the Insert Component command in the Property Manager tab on the left. These options help you start assembling quickly, but for now, I'll close them so we can take a closer look at the environment. As you can see, the layout is almost identical to part modeling. You still have the Command Manager, Task Pane, Manager tabs, and Graphics area. The three main planes along with the origin are visible in the Feature Manager design tree, just like in part modeling. There's also a folder called Mates beneath the origin, which we'll explain later as we move forward. Navigation works the same way as in part modeling, and many familiar commands, like those in the heads-up view toolbar, function just as they did before. For example, pressing the spacebar brings up the View Orientation command. Let's hide the planes for now to keep things clean. If you are new to assemblies, the number of available commands might seem overwhelming. To simplify things, I'm going to hide all the tabs in the Command Manager, except for the Assembly and Evaluate tabs by right-clicking on the Command Manager. As a beginner, it's essential to focus on two key tools: Insert Component and Mate, which can be found in the Assembly tab. Mastering these two will give you the foundation you need to tackle more advanced techniques later. For now, let's concentrate on the basics, starting with Insert Component. As the name suggests, this command is the primary method for inserting components within the assembly environment. When we refer to a component, we mean both part and assembly documents. An assembly can consist of just parts or a combination of parts and assemblies in the design tree. To insert a component, simply click on the Insert Component command. Just like when we first opened the assembly document, the Insert Component command initiates alongside the Open window, allowing us to search for parts and assemblies we have previously created. Now, if you accidentally close this Open window, you can reopen it by clicking on the Browse button in the Property Manager. Let me close everything to show you something more. Let's say we have a part document open in the background. I will use the Open command to access the base of my intended assembly. The document opens in a separate window, and you can navigate between open documents by pressing the Ctrl+Tab combination on your keyboard. This way, I can return to my assembly and initiate the Insert Component command once again. With another document open in the background, you can see that I can choose it directly from the Open Documents window in the Property Manager. I click once on the base document and then hover my cursor over the graphics area. If I press the left mouse button again, then the base will be inserted into my assembly. However, the position of my base will be arbitrary. To clarify, let's activate the origins from the visibility options. As you can see, if I click anywhere else, the component origin won't necessarily coincide with my assembly origin. If I want these two to align, I need to move my cursor to the assembly origin and then click the left mouse button when this symbol appears. Alternatively, you can simply click on the green checkmark at the top left of the property manager. This brings the base to the center of the assembly. With that to know, I am ready to insert my first component. But before I do that, there is an important option, especially for beginners. I recommend that you always insert your base component first and check the Only Fix First Component option beneath the Fix Float component on Insert section. This ensures that you have an immovable and sturdy object within your assembly, serving as an anchor for the other components we're about to insert. This step, along with your first component, is extremely important. Once we've done all that, hit the green check mark to insert the part at the center of the assembly origin. As you can see, the planes and the origin of the assembly document perfectly coincide with those of the base components. Let's insert a second component. This time I will insert a crank part. As you can see, all my parts are stored in a file location on my hard drive. For convenience, I use the same file location, but your parts might reside in different folders. This time, I will left-click in an arbitrary position in the assembly document because I don't need this component to be fixed in the center. In fact, I want it to be freely movable. Let's check the design tree to see more. As you can see, the components we've added so far are listed in chronological order in the Feature Manager design tree. A fixed component, like the base we have here, is marked with an F in parentheses. This indicates that the component is locked in place and cannot be moved. In contrast, a floating component, like the crank, is marked with a minus sign in parentheses, meaning it can move freely within the viewport. For this assembly, we want only one fixed component, which is the base. For now, let's hide the base. To do this, simply left-click on its name in the design tree and select the hide command from the context toolbar. You can also access the same hide option by left-clicking on the part itself in the viewport. Now let's take a closer look at how floating components behave in the assembly environment. In 3D space, an unrestrained object has 6 degrees of freedom, 3 translational movements along the X, Y, and Z axis, and 3 rotational movements around each of these axes. As long as no restraints are applied, I can move and rotate this object freely within space. But what if we want to limit this movement completely or allow the object to follow a specific path or motion? This is where the mate command comes into play. By applying mates, we can control the degrees of freedom, allowing for precise movement within the assembly. Let's click on the mate command and take a closer look at how it works. Once activated, you'll see several options in the property manager. While it may seem overwhelming, I'll break it down step by step so you can easily grasp the basics. As you grow more confident, you can explore the advanced options later on. First, notice the 4 tabs in the property manager. Depending on your version, these tabs might be located at the bottom and are categorized by mate type: Standard, Advanced, Mechanical, and Analysis. For beginners, I recommend sticking to standard mates until you are comfortable with assembly modeling. When you select a tab, you'll see a blue field labeled Mate Selections. This is where you'll choose the points, edges, or faces of the components you want to connect. For beginners, I suggest selecting faces most of the time, as this helps limit degrees of freedom. To begin, let's select the face on the crank component. Notice that the crank becomes transparent, indicating that we can't select another face, edge, or point on this component. This transparency also allows us to pick a face on another component that might be behind it. The key point here is that mates can only be created between 2 different components. Depending on how we want to connect the faces, we can choose from several options. It's essential to visualize how the components will fit together. For example, I want the crank to rotate around the cylinder of the base. So I'll select the concentric mate and then pick the cylindrical face of the base. This mate ensures that both cylindrical faces share a common axis of rotation. Once I choose that face, a few things happen. First, the crank automatically aligns to satisfy the concentric condition, meaning it's now properly positioned around the cylinder. A toolbar appears with options to either accept the mate or modify it further. After I press the green checkmark, the mate is confirmed and the command remains active by default, allowing you to add more mates if needed. For now, I will close the command so we can observe the results. If you expand the mates folder in the Feature Manager, you'll see the newly created concentric mate between the two components. Left or right click on it will bring up options to edit or delete the mate, and it also highlights the connected components, which is helpful when dealing with large assemblies. Now back in the viewport, let's test how this mate affects the components. When I hold down the left mouse button and try to move the crank, you'll see that its movement is now restricted. It can only be rotated around the cylinder while moving up and down. To refine the motion further, we'll need to add more mates. Let's initiate the mate command again. This time, I'll select the bottom face of the crank and the top face of the base. This automatically applies a coincident mate, ensuring that these two faces align perfectly. Generally, SOLIDWORKS can automatically choose which mate to use depending on your selection. So keep in mind that in the future you need fewer clicks to accomplish such connections. Now the crank can only rotate, which is exactly what we want. A rule of thumb for beginners only. Remember when I told you to use faces mostly? This is because of this one. If we wanted this cube to be unable to move at all, it takes only 3 mates to do so by utilizing faces. In cases like the crank which we want to rotate, we want to apply fewer mates. So keep in mind that if you use more than 3 mates while using faces, you might want to consider deleting a mate or 2. I tell you that because later on, you might come across error messages that you might want to overcome. And that's the basics of how to use mates in SOLIDWORKS. Let's continue by adding more components and mate them together. From here on, things are easy. You can either add all components together or one by one. I prefer the one by one method because it helps me with my demonstrations so we can focus on different aspects of the software. Let's see some special cases like this slider here. Mating it on the top of the base with a coincident mate is easy. But the best way to maintain symmetry here is to give a coincident mate between the right plane of the assembly and the right plane of the slider. The right plane of the assembly and the slider can be accessed either by going to the design tree on the left or by pressing the Q on the keyboard while hovering over the slider component. This allows us to choose the 2 planes that we want. Now the slider moves as it should, but we need to add more to complete this assembly. Let's insert the connecting rope. Just add 2 concentric mates on the crank and the slider. At this point, I want you to notice something. As you can see, moving any of the components gives the exact motion that our assembly should have, regardless the lack of the coincidence between the connecting rod and the upper face of the crank or the retaining rings that would keep it in place. This means that SOLIDWORKS obeys relations between components. It doesn't read minds to know that I want to create a slider crank mechanism. So at this point, it's a good opportunity for the designer to take decisions while the final product is still under development. Since we are okay with the design of this assembly, I will proceed by adding the final mate here. So if you know how to insert components and adding mates, you are good to go and begin working with your assemblies. If you're interested in learning more about assemblies, stay until the end because I'm going to show you some more tricks here. SOLIDWORKS Toolbox is an add-in available with the SOLIDWORKS Professional or Premium licenses and can be accessed from the task pane under the Design Library tab on the right. By clicking the green Add-in Now link, it loads a collection of components that follow common industry standards including ISO, ANSI, DIN and others. Let's take the DIN standard as an example. The DIN folder contains subfolders representing different families of components, like bearings, bolts, nuts, and retaining rings. For this demonstration, I'll select retaining rings, which are organized into categories like external and internal rings. You can navigate by clicking the arrows in the top left or use the navigation along the top. I'll click on the external folder, where we have 4 types of retaining rings. The power of Toolbox components is that you can simply drag and drop any component onto the viewport. This action not only inserts the component but also snaps it in place, matching its size to the nearest fit. After releasing the left mouse button, the Property Manager opens on the left, allowing you to further adjust the Toolbox component settings. Different Toolbox components offer different adjustable properties. For instance, a retaining ring has a groove diameter option, while a gear might allow adjustments for module and number of teeth. Once we hit the green checkmark, the new component appears in the assembly ready for reuse. We can continue placing the same component in different positions, but for this example, I'll only add one more above the connecting rod. This reusability speeds up the design process, while the component library eliminates the need to design such standard components from scratch. You'll see that Toolbox components are marked with a bolt symbol, and mates are automatically added to the mates folder. I won't go further into the Toolbox features, but let me know in the comments below if you'd like a more in-depth video on this topic. Now let's explore some additional capabilities. As I mentioned earlier, all mates are stored within the mate subfolder at the bottom of the design tree. Here, you can see all the mates I've added manually, as well as those automatically generated by the Toolbox components. To edit a mate, simply left-click or right-click on it to make a toolbar appear. From this toolbar, you can select the Edit Feature command. This feature allows you to make various changes to the mate you've created, such as altering the selected faces, adjusting the alignment, or even changing the mate type to something different. Once you've made your changes, click the green checkmark to apply them. While most cases can be addressed with simple mates like coincident and concentric, there are some additional useful mates I'd like to introduce. Let's start with a distance mate. The prerequisite for using this mate is to select 2 parallel faces and then set the desired distance between them. For this example, I'll set a distance of 50 mm between these 2 faces. If needed, I could flip the dimension by clicking the checkbox here, but in this case, I will leave it as it is. Keep in mind that this distance is a constant value. You'll notice that regardless of how I attempt to drag any component, the entire assembly remains fixed. To reset the motion of the assembly, you have the option to either delete or suppress the mate. Let's talk about suppressing. By left-clicking on the mate, you can select the suppress option. This action deactivates the mate, allowing you to move your components freely once again. Of course, you can suppress anytime you want. Before we explore the next mate, I want to highlight that you can also suppress components. Suppressing a component essentially makes it as if it never existed in the assembly. The key difference between suppressing a component and simply hiding it is that suppressing a component also suppresses any associated mates, resulting in a lack of motion. In contrast, hiding a component keeps the mates intact, allowing for continued movement within the assembly. Now let's return to where we left off so I can introduce another useful mate called the angle mate. This standard mate functions similarly to the distance mate, but it requires you to select two faces that are not parallel. After selecting the faces, you'll need to set the desired angle between them. You can input the value in the angle field and, if necessary, flip the dimension using the checkbox provided. Once you click the green checkmark, the mate is applied, effectively maintaining the specified angle between the two faces. When trying to fully define an assembly, you'll notice a status indicator at the bottom right of the status bar that shows the under-defined condition. Even after applying all the necessary mates, the assembly may still be underdefined. This often occurs due to the freely rotating toolbox components that have not been adequately constrained. Concentric mates can be locked to prevent unwanted rotation around the axis. To do this, hold down the Control key and select all the concentric mates you want to lock at once. Then, right-click on the last selected mate and choose the Lock Rotation option from the menu. This action ensures that the toolbox components can no longer rotate freely. You can also lock the rotation when you initially applied the concentric mate. When it comes to deleting mates, you can right-click on any mate to access the delete option. Alternatively, you can simply press the delete key on your keyboard. A common mistake among beginners is to leave unnecessary mates in the assembly even if they serve no purpose. So remember to always delete unnecessary mates. Depending on the version of SOLIDWORKS you are using, be aware that adding mates that conflict with existing ones may prompt you to either break the mates that satisfy the new one you're about to add, or create over-defined assemblies, resulting in paradoxical connections between components. This behavior is similar to how relations function within the software. To resolve these conflicts, you will need to either edit, suppress, or delete the conflicting mates to ensure your assembly behaves as intended. By unsuppressing the distance mate, you'll see that the assembly is now fully defined. Before we proceed to the evaluation of our design, I want to mention that you can add another assembly into our current assembly, which effectively treats it as a component. This means that any commands we've covered so far apply to the newly added subassembly as well. However, it's important to note that subassemblies lose their motion capabilities once inserted into another assembly. To allow the new subassembly to retain its motion capabilities, simply left-click on it and activate the Make Subassembly Flexible command. This enables the subassembly to move as intended. Conversely, if you choose the Make Subassembly Rigid option, it will turn to its last saved position within the document. To save your assembly documents, simply click the Save icon located at the top of the interface, just like you would with POT documents. It's essential to regularly save your work to avoid losing any progress. Now that our assembly is fully defined in a specific position, let's explore the information we can extract from it. This is especially crucial for those planning to take the SOLIDWORKS Associate and Professional examinations, because that is the way you get tested. For instance, let's say we want to measure a specific angle when the distance covered by the slider is 50 mm. To measure specific dimensions or angles in our assembly, we'll use the Measure tool, just like we did in the part modeling video. First, navigate to the Evaluate tab and select the Measure tool. When the blue measurement window appears, you can insert the two faces you want to measure. For example, selecting these two faces will display the angle between them. You can also measure the angle between a face and a plane by choosing one of each. If the two faces are parallel, the tool will provide the direct distance between them. Now let's calculate the center of mass of a mechanism relative to the coordinate system while it remains locked in position. To do this, we'll use the Mass Properties command, which can be found in the Evaluate tab. Before proceeding, there are a few important things to note, especially for those preparing for the SOLIDWORKS Associate or Professional exams. Ensure that your assembly is in a specific position with fixed distances or angles, meaning it should be immovable. In our case, we have a distance mate that locks it in place. Additionally, check the Report Coordinate Values Relative to field. By default, SOLIDWORKS calculates the center of mass relative to the origin of the part or assembly. This is crucial for accurate evaluations. Next, let's create a new coordinate system to facilitate our measurements. To do this, navigate to the Assembly tab and select the Reference Geometry command. Choose Coordinate System. In the Property Manager, start by selecting a point as the center of your origin, which is the common point of all three axes. For the X and Y axis, choose an edge on your model to orient the coordinate system properly. The Z-axis will be perpendicular to the plane created by the X and Y axis. You can also adjust the direction of the axis by clicking the arrows next to each axis. This is important as it defines the positive and negative values in 3D space. Once you are satisfied with your selections, click the green checkmark to create the coordinate system. You'll see it appear in the design tree. However, if you click in the empty space in the 3D viewport, it may disappear. This happens if the visibility of your coordinate systems is turned off. To resolve this, go to the Visibility drop-down in the Heads-Up View toolbar and activate the Coordinate System options. Keep in mind that this is distinct from the origins we discussed earlier. Now let's return to the Mass Properties. From the drop-down menu, change the coordinate system from the default option to the new one we just created. Notice how the values update as you switch between coordinate systems. If you wish to hide the coordinate system, simply left-click on it and select the Hide option from the context menu. But we are not done with evaluations just yet. To check if any components interfere with one another, we can use the Interference Detection command found in the Evaluate tab. In the blue field, select the components you want to check for interferences. For this example, we'll check the entire assembly. Next, click the Calculate button. In the results window, you'll see any interferences detected within the assembly. Clicking on any of these interferences will highlight the affected area in the viewport, allowing you to visualize where the components overlap. For instance, here we can see that the hole diameter is not large enough, resulting in interference. You can also click the arrows beneath each interference to see which specific components are involved in the highlighted area. If needed, you can right-click on a component to open it directly. Let's make the necessary adjustments by changing the diameter of the hole. Once you've made the changes, hit the Save button and close the part to return to the assembly. Now let's run the interference detection once more. This time there are no interferences since we've successfully fixed the diameter. Now I will suppress the distance mate once again to allow the assembly to move freely. If a component has multiple configurations, you can easily switch between them. Simply left or right click on the component in the design tree or in the user interface, and a drop-down menu will appear, allowing you to choose the desired configuration. Let's go ahead and change this configuration now. You'll see that the changes are immediately reflected in the viewport. If you don't notice the changes right away, just click the Rebuild button to update the assembly view. However, take a look at how the assembly behaves. As you've seen previously, during the interference detection, components can freely intersect with one another, which doesn't reflect real-world physics. We can leverage this to our advantage to explore the motion range and gather valuable measurements, especially when we are uncertain about the dimensions of our models. To do this, we can use the Move Component command with the collision detection option activated. As we move the components, any faces that collide will turn blue, and you may even hear a sound indicating the collision. Once we've established collisions, we can exit this mode by clicking the green checkmark. From there, we can take measurements using the Measure tool to make the necessary adjustments to our assembly. This video could end here, but there's an important topic that beginners often overlook. The following part could be a video by itself, and maybe I'll upload it as a standalone video in the future. Understanding how SOLIDWORKS documents collaborate and connect with one another is crucial for effective assembly management. Let's dive into how SOLIDWORKS Assembly references work, so if you encounter any errors in the future, you'll know why they happen. First, let's navigate to the File drop-down menu and select the Find References option. Here, you can see how an assembly document references its components based on their names and file locations. To demonstrate this, let's rename the crank SLDPRT document to something else. At first glance, everything seems to work fine. However, if you close the assembly and reopen it, a window will prompt you to locate the now missing file. This error occurs because the file is missing due to the name change. You have three options here. 1. Browse your machine to locate the lost document. 2. Suppress the missing document. 3. Suppress the missing document along with any other components that may be missing. For now, let's suppress the crank. As you can see, the component is marked as missing, and errors appear in the design tree. This situation can be stressful, especially in larger assemblies. Returning to the Find References window, you'll notice that the crank SLDPRT cannot be found due to the name change. If you select the Browse for File option or try to unsuppress the crank, Windows Explorer opens, allowing you to search for the missing part. Once you select the correct document, all errors will disappear and the assembly will return to its previous state with the name updated to whatever you renamed the crank component. However, the file location remains unchanged. If you save the assembly now, the new part name will be stored in the references. If you close the assembly without saving, the new name for the crank won't be stored. If you restore the crank's name to what it was, it will also restore any errors within the assembly. As you may have guessed already, changing the file location of a component, like moving the crank into a subfolder, will have a similar effect. To fix this, you would need to relocate the component by browsing through the Windows Explorer. This action will update the file location in the Find References dialog box. Again, saving the assembly will store the new file location, while restoring the missing component to its previous file location will also resolve any errors. Now that we've covered how the referencing system works, it's clear that both file location and name are crucial when managing external references. But how do we rename or move components without causing these errors? In Windows Explorer, you can right-click on any SOLIDWORKS document and choose the SOLIDWORKS sub-menu. Among the various options available, you'll find the Rename and Move features. These tools allow you to make changes without breaking any references, unlike what we attempted earlier. Let's start with the rename option. Once selected, you can give the existing component any name you wish. With the Update Where Used checkbox activated, you'll see a list of all the files that reference this document. When I click OK, not only does the part name change, but all files containing this part are also updated automatically. Now let's do the same for the slider part, but this time I'll use the Move option. Again, I can change the file location through the Move To menu, and with the Update Where Used option checked, all documents referencing this part will be updated accordingly. To see how this affects our assembly, let's reopen it and check the Find References option again. As you can see, the references have been updated with the new file locations and names. And that's how we can make these changes while avoiding errors. Mastering SOLIDWORKS may take time, but once you do, all of this information will become second nature. Feel free to revisit anytime you need a refresher. If you found this video helpful, don't forget to hit the like button and subscribe to my channel for more SOLIDWORKS content. Thanks for watching, and I'll see you in the next video.